We'll start our afternoon session with presentations on the modeling of the F-cube processes. The first presentation is entitled Connecting F-cube's Bioenergy Carriers, a Novel Supply Chain Model, presented by Haresh Jayasankar. Haresh is currently pursuing a structured PhD in mechanical engineering at the University of Galway, with the initial stages of his research focusing on the techno-economic analysis for carbon capture and transport in Ireland. Haresh, the floor is yours.
So good afternoon, everyone. I'm Haresh. Thanks for the introduction, Mike. And my topic is actually connecting FQ's bioenergy novel supply chain. So from the topic itself, you might say that it's about how we connect the bioenergy produced from the FQ process with the end user. Yeah, so the objective of my work is to develop a supply chain model for the intermediate bioenergy carrier produced from the FQ process. And, you know, we have waste residue such as paper biosludge, orange peels, and olive polymers. And we have the FQ process, and we have the end user. And what we can do in the middle is my objective. So before going into the actual results and methodology section, I would like to slightly show you a simplified FQ process. So that will make my job easy. So we have the wet residue coming into the feed conditioning, towage, and dewatering system. And then what we get out is the press cakes. So you might have seen in the other presentations. And I'll call this the FDD system. And once we have the press cakes, it will go through a dryer, and we have the dry press cakes. And then it will go through a pelletizer, and we have the pellets. So the main idea is to utilize these component configurations and then develop a supply chain out of it. So the methodology I used was develop possible configurations of the F-cube system initially using the components identified. So we have the FDD system, which is the feed conditioning, which is at the wet residue site, which cannot be transported. So I'm assuming that the wet residues are not transported, and it's at the site of the wet residue. And then using the other components, dry and the pelletizer, I tried to build configurations for the F-cube system. And then construct case studies. And within the case studies, build scenarios using the developed configuration and the other parameters. So we have the transport mode and the end use options and stuff, things like that. So build scenarios within the case studies so that we can analyze more depth into the case study. So conduct cost evaluation and optimization. And then finally, identify the best scenario. So we have the optimal condition identified, and we can use the cost evaluation and optimization to identify the best scenario out of it. So the parameters used for the case studies. For these case studies, I have two case studies. One is for the Northeast region, and one is for all of Sweden. I'll come to that. Before that, I need to introduce the parameters. So for these case studies, I used the wet residue source as paper mills, and the transportation method to be truck transportation, and the end user is to be partial replacement of coal in ore and reduction in steel mills. So, and there's one more parameter, which is the configurations of the F-cube system. So I have developed 4 possible configurations of the F-cube components. So you can see the green one is the FDD system, which is the feed conditioning, towage, and the dewatering component. Altogether, I call it the FDD component. And the red is the dryer, and the purple one is the pelletizer. And what we can do is, within these components, where we can place them and then try to optimize it is my goal. So the configuration one is it's the normal one, which is we have all these systems, which is the dryer, pelletizer, and the FDD system at the site of the wet residue, which in this case is a paper mill. And then we transport the pellets to the steel mills elsewhere at B2. And the configuration 2 is we have a drying hub at B4, which means we get press cakes out of the FDD system at B3, and then we transport those press cakes to the dryer at B4, which is a dryer which is placed in a paper mill elsewhere, and then pelletized and transported to B5, which is the steel mill. And the configuration number 3 is we have a centralized dryer, which is away from both the paper mills or paper mills, whatever the number. And this hub, the drying and pelletizing hub, is in a different location with respect to the paper mills. And we dry them, pelletize them, and transport to the steel mill. And the configuration number 4 is we have the drying hub at the steel mill itself, and then we use the dried steel, dried press cake or dry cakes, and then pelletize them and use them in the steel mill. So I did a study without the pelletizer or two, and then with the pelletizer. So we use dry cakes directly at the steel mill, or we use pellets at the steel mill. So there were two things, and the hub is like we have multiple sources coming to the hub. So I call it a hub because we have multiple sources of press cakes coming to the drying hub. So these are the parameters. So the two case studies were developed. One is for the northeast of Sweden. So considering northeast of Sweden, I have there were two paper mills to be considered. One is Smurfit-Kappa, and one a bit of north of Smurfit-Kappa, which is Billerud, and they're marked in blue. And there's a steel mill, SSAB, in Luleå, which is between these two paper mills. And that is for northeast of Sweden. And then I did another case study, which using all the paper mills and potential steel mills which have iron ore reduction. There are two potential steel mills as the end user, and then we have 21 paper mills around Sweden. And if you see, the northeast region is pretty much isolated from the southern or the central part of Sweden. Scenarios for the northeast of Sweden. So initial case study, like as I said, I was building scenarios for the northeast of Sweden, and the costs analysis were done with respect to Smurfit-Kappa. So there was 3 scenarios for the northeast region. So the region considered is northeast of Sweden, and end use is SSAB steel mill. So we only have one steel mill there. So the wet residue source will be like Smurfit-Kappa for the scenario number 1, and the configuration will be the normal configuration, which all the components are at Smurfit-Kappa, and the pellets are transported to the steel mill. And configuration scenario number 2, I integrated considered both the wet residue sources, which are Smurfit-Kappa and the Billerud, which is north of SSAB. And the configuration which is used here is where we have a Smurfit-Kappa and the drying hub at Smurfit-Kappa. So we transport press cakes to Smurfit-Kappa and then pelletize them and use it at the SSAB steel mill. And the configuration number 3 is, scenario number 3 is again same wet residue source, and then the hub is at the steel mill, which is SSAB. So these were the configurations which I developed, these were the scenarios which I developed for the case study, initial case study. And the result, before going to the results, so whatever you have in blue is for the total cost for pellets, which is processing cost, transport, drying and pelletizing cost. So I have considered 2 cases which I used a pelletizer and without the pelletizer. So we have 2 things. The end product is pellets, and the other one is dry cakes. And the lighter colors are the transportation cost. If you see the processing cost against the transportation cost, it is pretty low. And interestingly, the cost of dry cakes were equal to transportation cost of pellets. But if you see, if you see the transporting, dry cakes, you might have seen in previous slides, the density of dry cakes is very low compared to pellets. And it's about 325 compared to 750 for pellets. And if you see the higher heating value, they're similar. So why not use dry cakes directly than pellets? So, but the challenge there is whether transporting dry cakes will cost more because there's a lower density. But interestingly, the payload if we were able to utilize the entire payload of the truck, so which means we can transport dry cakes or pellets, it doesn't matter, the cost will be the same. So that's one results in the transport section. So we had a clear advantage of 25% cost increase when we produce pellets. So using dry cakes were cheaper, 25%. And introducing hub. So the initial scenario was all the systems were at Smurfit Kappa and then transported to the SSAB steel mill. And the second scenario was introducing a hub at Smurfit Kappa, where we take press cakes from the Billerud paper mill and then process it at Smurfit Kappa. So with the use of economics, here we get the advantage of economics of scale. So larger the dryer, lower the cost. And there was a 30% reduction in cost, because of the economics of scale. So here, what happens is the per ton cost of drying reduced when we had the drying hub introduced to the system. And similar to that, there was a 4% increase in transporting cost in scenario number 3, which means because we were transporting more press cakes to the steel mill at SSAB. So there was a slight increase in the transporting cost. So the outcome was scenario 2 was much cheaper compared to scenario 1 and 3. And now the all of Sweden case. This is pretty interesting. The goal was now we did one localized scenario, which is a localized case study, which is northeast of Sweden. But what if we have all the paper mills in Sweden considered and the potential end users located? So the idea was to identify the optimal number of hubs and their locations, the goal for the all of Sweden case study. And the challenge was handling nonlinear functions. So the drying and pelletizing cost depend on the economics of scale. And we all know that is to the power of something, so it's nonlinear. The function is nonlinear. And traditional supply chain algorithms, such as P median, they require the size of the hub and the quantity which is processed to be prefixed, and it only calculates the transportation cost. So there was a challenge, and it doesn't consider these economics of scale or the nonlinearity of this economics of scale when we consider the processing cost at the drying and pelletizing hub. So that was the challenge, and the methodology or the solution which I developed was I used a different algorithm called simulated aniline. So it's simulated aniline, so developed an optimization algorithm using simulated aniline, and the objective function of the algorithm contained the transportation cost, processing cost for drying and pelletization, and also the size of the hub. So depending on the size of the hub, internally within the iterations, it optimizes the best conditions. And the results. It's pretty colorful. I mean, I developed outputs for from 1 hub case to 21 hub case. So we all know that there were 21 potential paper mills in Sweden. So the 21 hub case is actually the on-site complete system, F-cube system at the site of the paper mill. So we have 1 hub scenario, 21 hub scenario. So the first hub scenario, so the 1 hub scenario, we had a hub in the middle of the country, and all the press cakes were transported to this hub and then dried at, and used at the SSAB. SSAB, which is south of Sweden. So both are SSAB, steel mills, and one is in northeast and the other one is in south. So that, connecting to that, the hub was connected to that steel mill. And for the, let's take the 7 hub scenario. There are 7 hubs in the country, and the hubs were connected to both the steel mills, and it's the amount of press cakes which is processed at the hubs. And then we have the 21 hub case, which is the on-site cases where every steel paper mill has, the complete F-cube system. And going into the actual costs, it was pretty interesting. The 2 hub scenario was the cheapest one compared to one hub scenario. Even though we utilize the economics of scale, we can observe that there was so much press cakes transported from northeast of Sweden to the southern part of Sweden. So it increased kind of the transportation cost, which is marked in green. And there was an 11% reduction in cost compared to the one hub scenario to the two hub scenario. And this is the two hub scenario, which is the map, which is in the corner of the screen. And when you compare the on-site scenario, which is to the 21 F-cube systems around the country, there was a 35% cost reduction when we have compared to the two hub scenario. And again, this is all because of the reduction in cost of utilizing the economies of scale of having a centralized dryer system. And you can see that the total cost of like pelletizing and drying increases with the high number of hubs we considered. And the other thing is no variation in producing press cakes, because the press cakes are produced at the site of the hub, and there were no cost variation in that, so they remain constant. These were so for the paper biosludge case, the conclusion, the primary findings were dry cakes are around 25% cheaper than producing pellets, and integration of a hub infrastructure results in a 35% reduction in overall cost. And the idea is like end product choice, optimized hub infrastructure for some component system lead to the reduction of cost. So I'll go quickly into the oligopomus case. So paper sludge is done, and we found that it is easy to have the hub scenario and have a product choice. Having a product choice reduces the cost. And for oligopomus and orange peels, it was pretty challenging because there were I developed three scenarios, like hypothetical scenarios, which is the first case is the actual techno-economic model which was developed for the oligopomus and orange peels, and I introduced the hub for the second scenario with a 10,000 ton dry matter processing hub, which uses which is a drying and pelletizer hub. And for the third scenario, the operation hours were increased. So in the first two scenarios, you can see the operation hours for oligopomus is like 960 hours per annum, and for orange peels is like 320 per annum. And for the third scenario, it was a hypothetical case, which we introduced like a 7,500 operation hour additional operation hour, which is like added from the 960 to 320, goes to 7,500. And it also has a hub. And the results were, for oligopomus case and orange peel case, the trends were similar. For the first scenario, there was an 18% reduction in cost when we introduced a hub, and there was a 87% reduction in cost when the operation hours in oligopomus case increased. And similar trends were seen in orange peels too. There's a 32% reduction in cost when we introduce a hub, which is a size of 10,000 tons of dry matter processing, and then a 67% cost reduction compared to the one hub scenario, on-site scenario, compared when we increase the operation hours. So the conclusions for the oligopomus case is oligopomus and orange peels achieve a significant cost saving, producing F-cube products up to 87 to 69% using large hub and with an extended operation hours. And a centralized hub with extended operation hours offer clear benefits. And seasonality of oligopomus. So the challenge is because of the seasonality of oligopomus and orange peels, it's a challenge because we cannot operate it 24. We cannot have a 7,500 operation hours. But if we can diversify the feedstock throughout the year, then I think achieving 7,000 might be possible. But it's a suggestion. Thank you, and hope you enjoyed the presentation. Yeah. Any questions? Yeah.
Any questions from the floor?
Hi.
Yes, I have two questions, but maybe to start off with the first one. Do you consider also variations in dry matter content? Because I can assume, because like now we have, like, for instance, for the paper sludge case, we have like a 40% dry matter content, but if it would reduce to maybe 50 or 60% dry matter, would it really have an influence on the number of hubs? Because then the transportation cost will be significantly lower.
So the density, the moisture content was considered, and the weight of the press cakes, dry cakes, and the pellets were considered. So I think the moisture content was considered. So the amount of dry matter in this thing, and it was clear that transporting press cakes were expensive compared to dry cakes and pellets. So they were considered, but I don't know whether to that depth. I mean, the moisture content, which were given in the reports, I used that moisture content in my analysis. So with the moisture content, the density and the weight of the transported products were it depend on the weight of the transport, products weight actually for transportation. So press cakes had a clear difference compared to dry cakes and pellets when we transport. Yeah.
Okay, and in one of your graphs or in one of your tables, I saw quite a big jump going from 13 to 14 hubs. What happened there? I'm just curious.
17 to 21 hubs.
Yeah, no, just really from 12 to 13 or 13 to 14. It was like no difference. It was a completely different color scheme.
Yes. So I analyzed between 1 hub to 21 hubs actually. So and identify the best hub scenario. So the optimal case was the lowest cost, which is the 2 hub scenario, and I showed you the 1 hub case, 7 hub case, and the 21 hub case. So it was the analysis, and then the final conclusion was the 2 hub scenario was the cheapest. Yeah.
Yeah, okay, but I mean, there was the table before, not the cost, but the one before. I mean, if it's possible to get that one.
Yeah. This one? No. Sorry, the hub case, This one?
Yeah, because here from number 13 to 14, everything jumps quite significantly. Yeah. Is there something... So what's the main difference between going from 13 to 14? I'm just curious.
So this is the 7 hub case. So this is the amount of press cakes processed at the hub. So if you see, there are 7, the column is divided into 7 pieces, and this is the amount of press cakes processed at each hub. So there are 7 hubs altogether in Sweden, and the quantity of total press cakes will remain constant, and the column is divided into 7 different hubs. So addition of that will sum up to around 50,288, and we have the 7 hub case, and we have the 2 hub case, which is, we can see before, the previous one was the 1 hub case. All the press cakes in the country is processed at 1 hub, and then we have the 7 hub case, and then we have the 21 case, where we have 21 F-cube systems attached to 21 paper mills in Sweden. And then this is the variation of press cakes variation. So actually the 21 is not a hub configuration, it's the on-site case where we have the complete FQ system attached to every paper mill. So this is not a cost analysis, this is actually the amount of quantity of press cakes processed at each hub. So there's a clear variation. So every, if you see from column number 1 to column number 21, the number keeps increasing. So 1, 2, 3, 4, 5. Yeah. And this is actually the cost curve. Yeah. Yeah.
Okay. But then going from 13 to 14, something completely changes between the processing per location apparently, because the big blue graph gets significantly shorter all of a sudden going from 13 to 14. So that was 13 just.
To 14. Yes, it should, I think, because from 13 we have an extra hub introduced to the system.
Yeah, okay, but from 7 to 13, it's constant. So I was curious what was going on there. So basically, you have a big change.
If you see if you see from 6 to 13, this is ordered in descending order. So we have the largest number on top and then the smallest number in the bottom. So if you see that after the blue, dark blue sides, one of the hub remains constant. One of the hub is not, one of the hub size is remaining constant. And if you see the lighter blue and the, whatever, the beige or something, it it changes, it splits. So one of the hub is unchanged. You can see that like from 15 to 21, it's the same. I think the biggest one is the Smurfit Kappa connected in the north of east. So it remains the same, and then it divides, the other parts of the things divide. So I have made actually, the graph was made in a way that we take the largest number on top and the smallest number after after that, because the colors might look crazy after that. Yeah. Yeah. Thanks, Millie.
Okay, thank you.
Thanks.